going to talk a little bit about Intent Media, the company I work for. We're a startup based in downtown. I promise this first section isn't a sales pitch, unless anyone's a chief marketing officer, in which case it's definitely a sales pitch and you can come and talk to me afterwards. What I want to get to is kind of an understanding of why machine learning is really important to us, right? And why the data science is really core to what we do. And then motivate some of the problems that we face, right, and that come up. And the two kind of actual things I want to talk about, one is a Scala library we built called DoubleSpeak, which is really around feature extraction, and kind of why we built it and what it aims to do. And then this kind of very natural pattern of you solve one problem and it's really successful and it leads to lots of people using it, and that leads to other problems down the line. So the next one was about having to deal with thousands of models that get changed very often, and so how we had to automate the pipeline. Okay, so first things first. Credit where credit's due. I didn't do a lot of this work, but there was a core team. There's a lot of other people around the edges, but I think these are the people who really did most of the work. And all the heavy lifting was done by Joaquim, Gabriel, and Sebastian. And in particular, some of this is Sebastian's brainchild. So if anyone has any really deep technical questions, see me in the office hours. And if I can't answer them, I'll give you these guys' emails. Yu Zhang and I are the data scientists, and like good data scientists, our role was mostly to like poke our noses in once in a while and make things extra difficult for the engineers. So, introduction to intent. Who are we? What do we do? So the basic premise of what we do is founded on the idea that almost everything on the web is optimized for the average user. And just like there's no such thing as a family with 2.4 children, that there isn't really an average user. But that's the way the world works. That's the way everything in our life works. And if we could undo that, if we could start optimizing for individuals somehow, we could do better. And you do better, hopefully, for the website, doing whatever your business metrics are, but also for the user. You know, you start to get treated more like you want to be treated. That's obviously a super great, lofty goal. That's great to say, but what do we actually do? So what we actually do is we've built a predictive intelligence platform which basically scores users real time on a site. And we return an intent score, which is something between 1 and 10, which can mean various different things. It comes as no surprise to this audience that this is the machine learning, this is the data science. And one example that's very common on a lot of our partners is what's the likelihood that this user is going to purchase on your site, right? That seems to be something most people care about, especially if you're a commerce site. So this is a kind of a good example, but it could be various other things like likelihood that they're going to shop somewhere else, likelihood they're going to book this other thing, likelihood they're going to bounce, likelihood they're going to stay on the page, and so on. I should say that, like, you know, 10% is good, but it definitely doesn't get you from the whole population down to an individual, but it's a step in the right direction. So like, it's allowing you to kind of treat users differently, and that's kind of what we're getting at. So the types of experiences that our partners are commonly using this for, imagine it was like the prediction was likelihood to purchase. Then if you're on the extreme high end of this scale, you give users a very commerce experience. You know, they want to book, you just keep things out of the way, keep it clean, maybe you get them straight to the cart quicker. And on the other hand, if they're not likely to book, then they maybe want to do something else, right? Maybe they're still searching and you want to treat them more like a search engine. And the media in our business was kind of where we found it, so we kind of provide an ad network, and that's kind of where a lot of the revenue comes in. And so you can kind of start to target the ads to the people who they're most useful for. This is just one example, right? There's lots of other use cases you could start to think of, and actually there's a lot of partners are starting to get kind of really into, you know, slicing up the data in different ways by these scores to do different types of things. Who do we work with? Well, we're definitely in the travel vertical for sure. We've got pretty good coverage in North America and Europe, and we're expanding out in Latin America and Asia Pacific. And the only real thing to take away from this slide is that we have a lot of searches, right? So we make these predictions a lot. So it's approaching 1.5 billion searches a month. Each of those searches is multiple events which have multiple predictions. So this is really something that happens at the web scale. So that's intent media as a kind of concept. How does data science fit into this? Like, where does it come from? And what do we actually do? So the data we use is collected from our partners, and so it's either a JavaScript tag on the page or a pixel that's dropped on it that fires events back to us. Those events are logged, and that log data is what we train on. So we'll train a model. So the example, predicting the likelihood to convert. These models are then used for real-time predictions. And when we say real-time, we mean real-time in the sense of page load time. Right? So there's obviously all networking effects. You've got to get this score back to the page and so on. But for just the predictions, we have an SLO of 10 milliseconds. So these predictions, the real-time inference has to be fast. It also has to happen at high scale and high throughput, right? So we're peaking out at about 160,000 a minute, and that's growing really rapidly over the last 12 months. So this has to be sort of very horizontally scalable. Once you've made the predictions, various things happen. One growing use case is we just pass the prediction back to the website and say like, hey guys, do your UX based on this. Whatever it is you want to do, you've got the data to do it. A lot of our partners, we will provide certain UXs based on that experience for them. So we'll show ads to the right people, or we'll show conversion boosting experiences. Maybe you get a promo code if you're on the fence, things like that. And then in addition to working out what type of UX to show, then like there's subtypes. So which type of ad are you going to see? Which type of promo code are you going to see? And those are all the sort of decisions that have to happen real time. And the real emphasis I want to make here is that this is all what powers the business, right? None of Intent Media would have been possible without this. So it does sit sort of at the very core of what we do. Okay, so background stuff aside, the thing I want to talk about first is a Scala library we built called DoubleSpeak. And it does feature engineering. And so one of the challenges we had was building and testing features rapidly, right? We want to try out a feature, we want to see if it works, and we want to get it out there. And I'm going to talk you through how we do it now with DoubleSpeak. And I'm also going to point out a problem that comes from versioning features and trying to serve models and publish models real time. If you've done this before, this will be kind of very familiar. If you just haven't done that publishing step very often, it's something you might not have thought about. So when you think of feature extraction as a step in a modeling pipeline, what do you want it to be? Well, the software engineers in the room are going to want it to be robust, right? We live in a real messy world where data comes in, it's incomplete, you've got nulls all over the place, right? You want to make sure it's robust to all these things. It should be production level code, right? This shouldn't be something that like I as a data scientist have hacked together in 10 minutes and then I'm going to put it up there because it worked on my laptop, right? It needs to be core code, so it should have all the things you want. It should be maintainable, it should have continuous integration, it should be things like that. On the other hand, as a user, I definitely want to be able to do this quickly, right? The whole point of being able to do this is to rapidly experiment and get things wrong 10 times, but at least the 11th time it works, right? And if each one of those times takes a month, this is going to be a problem. It should be flexible so that the types of events that we're getting, I don't want a different feature extraction for each of them. I want to be able to like reuse the code I've used over and over again for different types of feature, or different types of events. And I want it to be feature rich because at the end of the day, I'm pretty lazy. I don't want to have to deal with interpolation by hand every time, right? I'm used to using sklearn, which has all these fantastic features in there, and I want all of them. Those two things are very different sets of requirements, and actually finding one that does everything together is surprisingly challenging. But the other thing that's challenging is making sure this works fast at inference, really fast. So we built DoubleSpeak. So DoubleSpeak is a Scala library. What it does is define a feature extractor set, and I'll talk a little bit about what that is in a second. And you can use this basic object to extract features from RDDs. So if you're not used to Spark or Scala, RDDs are kind of one of the distributed data systems they have. But it can also be used for individual records real time. And the key point there is that you can use it to extract features from individual records without Spark. So you don't have to build Spark into your real-time inference section. You get some things for free. Free in the sense that you already had to do them, so you may as well output it. So you can encode all the features from batch jobs, and you can see what those are like. And you can get all these feature summaries, and you can see, how often certain categorical features appeared and what this, the averages and stuff are. This is very much like the .describe on a Panda. So I'm going to show you some actual code. When I say this is easy to use, I really mean it's easy to use because I'm the barrier, because if it's not easy enough for me to use, then they have to fix it. And it comes with a whole load of all the things you want, like imputers, transformers, normalization, and stuff like that. And actually almost all of that's built in as defaults that you can then override. And it leads to very concise code. If you haven't seen Scala, just read this as pseudocode. You don't need to see the details. This is the basic object that you build. Okay, so it's a feature set. Scala is strongly typed, so you have to give it a type of the object it's going to apply to. So in this case, it's impression. It's just some object that contains the data you're going to pull your features from. I gave as an example this validators thing here. Actually, as it happens, single value is a default, so you can ignore it. But you can put something in here that says, ignore features that have this property. So if there's a feature that you get and it's always the same value in the training set, just drop it. Don't even worry about it. If there's too many nulls, get rid of it. And then on the next 3 lines, we've got 3 features. The first one's a categorical feature, there's a numerical feature, and there's a binary feature. And all you need to define is the name of the feature, and the second argument is the function that returns the value of that feature. As an example to explain kind of what else is available if you wanted, you can override the default transformers for a categorical and say, well, how are you going to encode this? But you don't need to. And you don't need to specify normalization or anything like this. And in a single line, you've defined a feature extractor, and you can have as many of these as you want. And it really is that easy. So if I have an idea for a feature, it's one line of code, and I can write it down in about 10 seconds. Some nice features about this. Some of this is to do with DoubleSpeak, some of this is to do with Scala. But one thing that's very nice is this is being strongly typed. It means it's very robust to schema changes. So if someone changes something about the impression type, someone changes, I think earlier we talked about int going to string for some element of it, or someone adds an element or removes an element, this will all fail at compile time. So you don't have to worry about runtime errors coming at you. It's robust in another sense that if you have a categorical that a value for a categorical that you see in real time that you didn't see in the training data, it'll just default it to this other category, and that's actually how you roll up a lot of the long tail categoricals. That long tail is big for us, that we have a lot of categoricals that are extremely high cardinality. So you can think of like airport codes. There are tens of thousands of airport codes. And if you think of origin-destination airport codes, suddenly you're talking about hundreds of thousands of categories, and that has a very long tail. It has all the kind of default encoding and interpolation and normalization that you want, so you can just use it out of the box. You don't have to like start putting in stuff by hand, and you automatically get these feature summaries, right? So, and I say automatically in the sense that it has to calculate things like the mean and the standard deviation to be able to do normalization, so you may as well output them and be able to see them and look at them. It gives you a way of debugging features quite efficiently. So that was like the one piece was just this feature set, and I sort of said this is the core to it. How does that actually, like, what does it look like if you were using it for something real? So the color coding here is anything that's red is DoubleSpeak, and the rest of it's just bog standard Scala code, right? There's nothing special about it. So we've defined this feature set for these three nice little features, and that was the basic thing we needed to do. What you need to do next is load in an RDD of these basic data. This is your training data that you're going to test on, or you're going to train on. And then there's a DoubleSpeak function called RDD extractor, which you pass this feature set into. And that can apply to an RDD. And all it does is produces for you an extractor object which has in it a data frame ready for use in predictions, or ready for use in training. So the last two rows are just taking that training data set, joining it to whatever your labels are going to be, and then hitting train. So it really does kind of fit very nicely with the MLlib world. So this object, this thing that we get, this RDD extractor, what's in it, right? So there is the raw features. That's really just if you want to look at them and you can kind of do some analytics on it. And it's kind of useful sometimes to say like, hey, I've got this complicated sort of, structured object, like an Avro object or something. It's hard to reason about. If I turn it into a data frame, I can do all sorts of cool analytics with it. The reference features are the thing that you actually plug into a training, and it's just basically got this features column at the end, which is the vector, the feature vector that you're looking for. For this example, I turned off normalization just so that like you can kind of see how the one-hot encoding works, but you get the picture. This is just the features column that you're looking for. And the other thing it produces is an extraction metadata, and this is all the things like what categories did I see for a particular categorical, what was the encoding for it, what was the mean and standard deviation if I'm using standard normalization for a particular value, and so on. And those are nice to have from a kind of debugging point of view, but they're actually necessary to be able to test and do inference with. So we'll see how that comes later. So this was the training. How does it work when you want to test it? By test, I mean batch testing. So it's almost as simple, right? You have this object, there's a .extract function or method on it, which you can apply to other data. And the key point there is that this extract method uses the original category, the original categoricals, the original normalization from the training data. And this is where you can get things mixed up if you're kind of not concentrating. This is where you can accidentally only use categories that exist in the test data, not in the training data, things like that. So that's super easy. The whole purpose of doing this was really to focus on the real-time inference. So how does it work at kind of real time? One of the things we wanted to avoid was having to have a Spark dependency in the real-time world, because it really feels overkill to have a single event come in one at a time, load that into a Spark object, spin up the whole Spark sort of dependency, and then just to make a single inference on it. So it's almost as simple. You will load this metadata, which is this sort of artifact that we had, that gets loaded with the model. Okay, and we'll talk about how this model gets published and the metadata goes with it in a second. And from it, you can apply a record extractor method, right? So this is just for a single record. I want to extract features. And that is something that is built out of that metadata. And once I have that, I can apply a single impression. I get whatever it happens to be, a vector in this case. And that vector is ready for pushing into a serialized model, for example. Cool. One thing, and I don't know where the link is. Somewhere in here is linked to a Spotify code, the open source code, that does something very similar called Featurean. I highly recommend everyone looks at it if you're interested in any of this, especially since that is open source and this is not yet open source, so you don't have much of a choice. I just wanted to point out the kind of key differences. So first of all, the Featurean code is much more feature-rich. They go into a lot of natural language stuff. They have a lot more kind of features built into it, so it's great. This was geared much more to getting the real-time inference stuff sort of super fast. That was really the core to doing it. So when it comes, we're discussing open sourcing it, and it'll be a discussion next year as to whether it belongs as a separate thing or whether it's just additional functionality we put in there. So I want to kind of emphasize how successful this was as an engineering product or an engineering effort. So the old way of doing feature extraction was like just building the functions and testing them extensively and then having it there, and then once you've got one, you've got another one, and another one, another one, and then trying to wrap them all up together and trying to make sure all the vectors were consistent and so on. Which was painful, right? We ended up having about 10,000 plus lines of feature extraction code, and when we translated that all into DoubleSpeak with just the same features, it went down by an order of magnitude. Bigger, and more importantly, the number of test lines of code that we had to support those features went down from like 45,000 plus, and I still don't think we had proper coverage, down to like less than 3,000. And that gets it small enough that you can get your head around it and you can kind of really reason about, you know, are there big gaps? Is there anything we're missing? Are there any edge cases that we haven't covered? And as a user, by far, the biggest thing was to get a new feature into production went from an effort of days to weeks to minutes. So I can code up a new feature that I've just decided, hey, I think this is going to be great, and assuming I've done some analysis and think it's a good idea, I can kind of one line of code and commit to Git, and the whole continuous integration process happens, and it'll be pushed to production. Which is amazing. That's exactly what we wanted. Really fast experimentation. You know, try lots of things. Some of it's going to stick and work, which is fantastic. However, it leads to this massive headache from an operational standpoint. And the headache is now you've got lots of people like me changing the features all the time, so the models are constantly changing. And so you have to deal with that, right? You have to deal with the being able to publish and deploy models very rapidly all the time, and making sure that the model versions and the feature versions are in sync. And that's something that if you get wrong, you get very wrong. So let's talk about that. Let's talk about what happens when you think of features. I offline trained some built some features, trained a model, and I want to deploy it. How does that process work? So typically, these are the steps you think of in an offline training world, right? I load some data, extract some features, I train a model, I'm going to do various things to it, like test it and validate it and stuff. But assuming things are good, I want to push that model up to production. And in our case, production is some prediction service that, dealing with the prediction requests and the inference. The two steps, extract the feature and train the model, are distinct steps usually, right? And they're they're distinct steps at the real-time world. You need to find the right model, and I'll talk about why we have multiple different models in a second, and you better extract the right features for that model. And in case anyone hasn't thought this through, I'm going to do a really trivial example of why this can go wrong. So imagine we have the blue model up in production, it's constantly serving, it's good. It happens to be super trivial. It's got 3 weights, or 6 weights, and it's expecting a 6 vector. Right? And if I give it a 6 vector, it'll make a prediction and everything's good. Meanwhile, in the offline world, I've retrained the model, and for whatever reason, I now have a model that only takes 6 weights. Maybe I've lost a category in a categorical. Maybe for some reason I decide I'm going to delete a feature, and I don't need that feature anymore. Now I've got a feature extractors that will produce a 5 vector and a model that's expecting a 5 vector. And in production, in currently serving models system, I have things that are expecting a 6 vector. And you see immediately that the only way to push this to production is make sure they're always in sync, because if you ever try to do one first and then the other, you're going to end up in this period where something is just not consistent, right? You're either giving it 5 weights and a 6 vector, which, if you made things robust, isn't going to fail, but it is going to produce nonsense. And that's kind of worse than failing, because it looks like it's a prediction, it looks like it's working, but it's actually just complete crap. And that inconsistent state persists until you manage to push up the version of the features that go with the model. Now, this kind of deployment problem wouldn't be the end of the world if it was one deployment, happened once in a while, and it was only going to take like a few seconds to go up, and you'd be like, okay, it's a few seconds of inconsistency, but you know, it's something we can deal with. The challenge we face is it's not once in a while. We have thousands of models, and we deploy them every day. And that little bit of like inconsistency during a deployment can be like absolutely killer. So the key takeaway here is you really do need to keep the feature extraction and the model that you've trained in sync, right? Those really have to be part of the same process. They can't be different. And so DoubleSpeak helps us a little bit in the sense that the feature extraction code is all static Scala code. So when we deploy something, all that feature extraction logic goes with it. And the only thing that's left that you need to load is the serialized model and the accompanying metadata that the features are built from. So as long as you keep the metadata and the serialized model together, now you can be sure it's going up consistently. Now that's not super trivial, right? But at least it's kind of encompassed what you need to keep together in a very concise way. And it's all serialized, right? So you don't have to worry about too much about different pieces of code getting up in different times. Okay. So this is kind of one half of the talk. This was all on the feature extraction side and the kind of library we built to kind of help us do this and stuff. One of the challenges that we were facing before all this was a proliferation of models, right? So we were going from like originally 10-ish models to hundreds of models. We're now at thousands of models, and all these models retrain every day. So, you know, low thousands of models, they all get kind of configured by hand. Once they're done, you schedule them and they go. You can kind of keep track of that as a group, just. But when you do that, and then you've added on top of it that number is growing, and all of them are constantly becoming very different because people like me are adding different features and changing features, it becomes a configuration nightmare. And just keeping track of what models are where, what partner used what model and what the result was, and this one failed, and I don't know how many days it failed for, and I don't know what was actually used to make the prediction, becomes a real challenge. So why do we have lots of models? That's the first question, right? Why don't we just produce one model and predict on that? Right, that would solve the problem. So unfortunately, we don't live in that world because each of our partners, we need to train a model for them themselves. Right? Partners are usually pretty stingy about sharing data, so they definitely don't want different people getting a model trained on their data. So every partner gets their own model. Now that first slide where you saw lots of partners or whatever it was like 300 and some. Like cool, 300. I mean, okay, that's a lot, but it's you can deal with it. The real problem comes from the fact that not every partner gets just one model. So each partner could ask for a model for, let's say, a user's likelihood to purchase a hotel when I see them on my flight's path. And that starts to explode pretty quickly. It gets even worse when they say like, oh, I want that, and I also want to know like, what's the likelihood that they're going to bounce? What's the likelihood they're going to have another page view? What's the likelihood they're going to do something else and something else and something else? So the number of these models kind of goes up combinatorically with the number of partners, the number of different products, the number of conversion products, the number of models you're trying to serve. So we have thousands daily. If they were all qualitatively the same, that wouldn't be the end of the world. If there was kind of one universal set of configurations you could use, right, the rest of it becomes a scheduling issue. Unfortunately, that's not the case either. So you can totally imagine the amount of data you need to train a model is going to be very different from an Expedia of the world to some small European site, which has very low volumes of traffic. So there's some like cleverness you need to do to just work out what's the right amount of data to use for each model. But it's something you can kind of get your head around and figure out what to do. So that's kind of the length of the training data. Different models actually use different features, right? So now we have like really distinct models. They're very different from each other from a kind of functional point of view as well. They have different objectives, right? The different model types we've been talking about. This is, what Expedia considers a purchaser involves some implicit look-ahead window, right? A purchaser when? In the next 24 hours, next 10 years? I mean, those are very different things. And different partners have different definitions. So actually, almost every part of the model is different for different pipelines. And then finally, different algorithms, right? Maybe you try a simple model and it works really well, and something like a logistic regression is perfect, obviously use the simplest one. When it doesn't work and you've got to use something smarter, like you've got to go to like a gradient boosted tree or so on, like whatever it happens to be that works, that's the one you're going to use. But now you have lots and lots of different algorithms that you need to keep track of as well. And if all this was a one-off for each of these things, that would just become your day job. You do this every time, and you push models out, and they'd never change, and you were good. It'd keep you busy, but it wouldn't be very pleasant. But the real killer is that all of this has to repeat every day. right? So we don't live in an online training world. We batch train and then publish the models, and to keep things fresh, we retrain every day. Which means we have to worry about the deployments of thousands of models every day. And so the challenges we saw about publishing models and getting everything in sync and not messing it up become quite exacerbated. So here's the kind of picture to have in your mind, right? We have this kind of standard training pipeline. I'm going to talk a little bit more about how we kind of schedule these things and so on. We're an AWS shop, so you can play a game of guessing what the symbols mean on the side. So these are the sort of modeling pipelines, and I put hundreds here, we have thousands of them live at any one time. And the basic steps along the way are load data. We better load the right data that can be different for each of these pipelines. Extract features. The features we're using is different from each of the pipelines. Train the model. Well, the definition of the objective and the algorithm can be different from each of the models. Test the model. The actual definition of what is a pass, what's good enough, can depend very much on the partners. So really the only thing that's common to these pipelines is the publishing step, right? Is to actually go ahead and use it, or not, right? Maybe you decide this one wasn't good enough and you're not going to do it. So what did we do? Oh, sorry, this was all in the offline world. There's an exactly similar problem on the online side of things, right? When it actually comes to the online inference. So this has to be fast and it has to work at scale. So we use ECS to kind of horizontally scale. But every time a request comes in, some things have to happen. So you need to find the model. Right, so a request comes in from a partner for a particular product, for a particular prediction. You got to find the right model for that. You got to find the right features that go with that model, and then you got to make the prediction. And making the prediction means you got to remember what the algorithm I'm supposed to be using is to make that prediction, and all that has to happen fast. And so these are the challenges. This is why we kind of had all these thousands of things. This is why it became difficult. And so we decided to build something. And one of the reasons I want to just leave you with before I start talking about what the actual infrastructure looks like is like the scale of some of these things. So the training is big. I mean, it's not Google big, but it's still tens of terabytes of training data every day, right? So that's a lot. We have thousands of models live, right? So that's a lot of models to keep track of. It also means that when you get into the thousands, you're starting to expect some to fail, and you have to work out what you're going to do in those failure cases. The predictions have to be fast. So I don't want to try and pretend that like our response times to the website are 10 milliseconds, but like our prediction response times internally is 10 milliseconds. That's our SLO. And we have to deploy, I mean, essentially 100% of our models get redeployed daily. And the only exception would be to that would be ones that actually get deployed faster than that. So if something changed or there was broken, you wanted to deploy it in addition to that would be. And the last thing is all this has to be very robust, because a failure to make a correct prediction is kind of a really bad thing in the context of what we do. So, and you can imagine, imagine you're a partner out there and you've decided you're comfortable serving ads to people who are predicted to be low value. If we start predicting everyone to be low value and they start seeing ads and they were about to make a purchase, that's going to really hurt you. And the other way is just as bad, right? If you start saying, hey, all these low value people are going to start getting conversion boosting experiences, that's just a total waste of time and effort and money that you're not going to want to spend. And if our partners have integrated with these scores and put it into their like sorting algorithm or their search results, or they're using it for email retargeting or whatever, that starts to go very wrong very quickly. So we need to be quite robust and make sure that we're always serving whatever is the best prediction we can, and also understand that if we can't serve a good prediction, we know and we know what to do about that. So this all prompted like dealing with a modeling automated pipeline. And this is something we've kind of been working on this year. And we finished it up now, but like the system prior to that worked, and it was consistent. It was just extremely painful manually. There was a lot of PagerDuty stuff going off, and it's kind of like several teams. This was their whole job, trying to keep this sort of thing afloat. Modeling automated pipeline has taken most of that manual effort away from us, thank God. So we use Airflow. It's funny, I was expecting to have to try and convince people why Airflow is a good thing, but it seems like every third talk up here has used Airflow. So Airflow's great. I suggest anyone uses it or hasn't used it, take a look at it. We use it basically for the core scheduling and just coordinating what's going on, the different steps in it. One interesting thing we found is, we have thousands of models to train, and that's a long way from every possible model. But the coordination effort in trying to decide which models were going to go and what happens, someone wants to add a new model, and an account manager comes in and says, I want to tweak this model and so on. It turned out just to be easier to train every possible model that was supported by the data. And that leads to a compute overhead, right? So we're wasting money on AWS costs, which makes AWS happy, but it actually saves us a huge amount on the tech ops side, and it warrants the expense. The other benefits are it just means that if anyone wants a new model, it's there. It's already been done. I'll tell you a little bit in a second why we split these up into cohorts of training jobs. It's a very practical reason. Anyway, the first step in this is this prep step, which is basically, okay, go build up the jar, which has got the latest feature versions, the latest code. This is the thing that's going to get deployed. Stick it up in S3 so it's ready to use. It also goes and looks at our data warehouse and says, okay, what data do we actually have? The last X number of weeks of training, how many of the events that we're going to train on did we see? How many of the objective events did we see for every site, every partner, every combination of things, and which ones of these is actually sufficient to build a model on? And then go ahead and train those models. So once we've worked that out, we split these things up into cohorts, and the cohorts is really just to try and get like roughly equal-sized number of training jobs to go, and we train on Spark, and then launch those training jobs. So we use Amazon's EMR, which is the Elastic MapReduce clusters, and we just basically, for each of these modeling jobs, we spin up a new Spark cluster, train the model, and have the outputs pushed to S3. And the last thing then is the publish step, and the publish step is, if everything works, it's trivial. Everything works, it's just go ahead, push this thing up to ECS, the jar up to ECS, and all the new versions are ready, and everything's been versioned and kept in sync. The only logic that's required here is actually very important logic, is what happens if one of them failed, or some model didn't reach some validation threshold and it wasn't good enough. So for example, what happens if Expedia Japan hotels failed? What's the best alternative model to use in that case? Is it Expedia Japan flights, or Expedia US hotels, or some totally other model that seems like unrelated but turns out to do very well? Or is Expedia Japan hotels just so important that we should fail out completely, stop the whole deploy process, fix it, and find out what's going on? And that logic is all kind of being encoded into this in publish steps, so we kind of have hierarchy of fallbacks and so on. So here's what the whole architecture looks like. Like I said, we're an AWS shop. We use Airflow, just really kind of kicks things off and coordinates and keeps track of what's going on where. Snowflake's our data warehouse. It's great so far. It's been a real cost saver for us. So the steps along here are the first time you hit Airflow hits S3 is where it publishes the jar. Sorry, it wraps up the jar, pushes it up to S3 so it's ready to use by EMR. It then kicks off a whole series of EMR jobs. And in theory, you could just go, here are my 4,000 models I want to train, go train all of them, and it would spin up 4,000 EMR clusters. It's a good reason not to do that, so instead we do it in chunks, so kind of roughly equal-sized jobs. Each of those goes and reads the jar from S3, does the training, does the testing, does the validation, and then pushes the artifacts back to S3. Airflow then comes and says, okay, keeps track that it's happened, these ones have finished, when the next cohort's ready to go, it pushes up the next cohort, and it goes through the whole training process. And all the results of these things also get pushed to Dynamo. That's really just for our monitoring. That gives us a kind of a persistent view of what model happened when, what feature versions were used, what did the feature summaries look like at that point, what was the accuracy, and so on. As well as the decision about whether or not this model was going to be used, and if not, what was the other model that was used in its place. So this is the kind of governance piece of it so that we can keep track and go back and say on Thursday last week what happened. And finally, the publishing step, we just go and deploy this jar up to ECS, and all the model versions and everything with the corresponding metadata from the features are in S3 ready to be cached up. And this is the piece that kind of keeps everything in sync. The main key point here is that Airflow will fail the whole process if any piece of it needs to fail. So if some really important partner or some really important model failed and we're uncomfortable with publishing that, without having that model up, the whole deploy fails, and so it's a consistent, or at least an atomic deploy. Just as an aside, we also have this ability to push that same code to Lambdas. We use Lambdas quite a lot. And they're great for small-scale experiments. Right? So if you wanted to push the code up there and then you wanted to test against some small slice of production traffic, basically as a last A/B test before you go live with something, this is a very efficient way to put something up and tear it down without influencing the rest of things. We did toy with just using Lambdas for everything. It works, it's effective, it's just quite costly. So in the end, ECS is cheaper. Okay, and I think this is my last slide. So just some things to kind of keep in mind about what we like about this. So one actually that really relates to the last talk is that this is the production environment. This is the production code, like the production infrastructure that we use. But as a dev, I can toy with something and I can use any piece of it. So all Airflow is doing is saying, go trigger this thing, go trigger this thing, go trigger this thing. I can trigger any of those pieces myself. And we have like staging environments where you could spin up the whole end-to-end thing. And you have dev environments where you can push up any bit of it. So if you want to do an ad hoc training run somewhere and see what happens, you can totally do that from your machine in one command. You can push to lambdas, which is a nice to have. The key one for us is like this will automatically infer what correct model configurations to use, at least as much as possible, right? So the right amount of training data to use and so on is something that can be automatically inferred. And a lot of the other configurations that go with it are just dealt with by try all configurations. It's kind of like the hyperparameter tuning version of this. We define the fallback logic. That's something that's the business logic that we have to put in place. But it's defined, and it's kind of defined in one place, which is nice. And it also guarantees that every request will get a response. And that response is the best one we could give you at the time, and we know what happened, what that response was coming from. So I promised to explain why we break things up into cohorts instead of just spitting out thousands of Spark clusters on EMR. The main point is EMR is a shared resource, and AWS will throttle you if you do too many of them. That would be fine if we were the only ones getting throttled, but meanwhile our data pipelining folks also use EMR, and getting throttled as a company is a pretty good way to get unpopular quickly. So keeping the number of jobs you're spinning up to a manageable size is a good idea. It also improves maintainability. So if you start to see problems, you don't have to worry about spinning up the rest of them. If the first 6 fail in a row, you may as well not carry on with the rest because you know you got something wrong. The key point here is we keep a persistent, consistent record of every model and every feature version and everything that went up so that we can always go back and look at it. Actually, one of the things we're building right now is just making that kind of nice, with some nice integration for monitoring and alarms that go off and having some nice visuals and so on around it. And the key point I want to leave you with is this is a way of making sure that the deployments are atomic, right? If anything fails or you've decided it doesn't meet your business needs, you could just fail the whole thing and you don't end up in some weird half state where some of the things are predicting on the old version and some of them are predicting on the new version. Okay, and I think that's all I have. Happy to take questions.
I'm still a little confused by what you mean by train every possible model. So is that like you have hypothesis A, hypothesis B, you test them, and they both seem okay, and you productionalize both? Or is it like, oh, you have 6 features for a model, and then you're going to train for every permutation of literally those 6 features?
That would be awesome, and my AWS people would love that. No, we don't quite do every model. That's totally true. When I say every model, I mean so for every partner, there are a maximum of 4 or 5 products typically. So hotels, cars, flights, and cruises are the ones we have to deal with most commonly. And then there's every possible combination of those 4 and those 4. So there's 16 combinations of things for each partner that you have to do. Not all of them may be actively used, but it turned out to be easier just to train all 16 models and only use 3 in product, only serve requests from 3 than it was to worry about which of the 3 were being used for this one. So when I say every model, those are the configurations I mean, not the features for sure.
Other questions? You can just use that mic right there.
When you say you save the model, do you save the binary object or do you save some text instructions or something like that?
Yeah, great question. No, we serialize the model. So what goes up is a serialized model, and then what comes out of the record feature extractor is a serialized feature that's applicable to that model. Yeah, absolutely. We don't try to deploy the models. Actually, that would be extremely difficult for us because all the models can be different. In the old system that we had, that's kind of what happened, that the model was part of the static Scala code that got deployed, so in a sense it's the binary, and that meant you had to use the same features and the same model for everyone all the time.